Okay guys, this is Lewis structure for Covalent. I will probably erase some of this, so if I'm erasing you can fast forward, but I'm going to leave this side on here, but I need more board space, so make sure you have this stuff written down first. So Lewis structures for covalent compounds. Because we share, we're going to use lines and stuff, but we can form in a covalent bond a single, double, or triple bond. The higher amount of bonds you have between an atom, the stronger your bond is. So a single bond is less than a double bond, which is less than a triple bond. So triple bonds are very, very, very strong. So Lewis structures show atoms bonded and the unpaired electrons. The electrons like to be paired up for stability, and so we will actually be showing more lone pairs, which is the ones that are not bonded. So I'm just going to double check, make sure I got everything here. Yeah. So show atoms that are with bonds and the unpaired electrons that are not paired up with something from another atom, and we call those the lone paired electrons. And they do like to try to pair up. So that's the whole concept of a Lewis structure, is to show a model of where the bonds in a covalent bond are. Because remember, in ionic, they transfer, but in a covalent, they share. So let's go ahead, and I'm going to go ahead and make sure you have this down. So pause the video if you need to. I'm going to go ahead and erase this. So you can fast forward me through me erasing this, if it will let me. So I can have the board space to show you the next part of this video. Okay, so while this dries, I'm going to go over here. So count the total. The first thing we're going to do is count the total number of valence electrons. Remember, no atom has more than 8 valence electrons. So we're trying to get a complete octet. Second thing you're going to do is find the least electronegative and put it as the central atom. So remember those arrows that we drew on electronegativity? That's kind of where we're going with that. So which one is the most electronegative? Goes on the outside. The one that's least electronegative goes on the inside. It's the central atom. All right, and I'll show you that in just a second. And then we're going to draw single bonds between the atoms, central atom, and all the surrounding atoms that we put attached to it. We always start with single bonds and then we increase. You check for valence electrons. Okay, so you're going to check for valence electrons to use them all. And I'm going to go through this. We're going to do carbon dioxide as an example because it kind of covers all these rules. Okay, so we have CO2. First thing you want to do is count the total number of valence electrons. So how do we do that? Well, we're basically going to, what I like to do is I say, okay, we have carbon. I have one of those, and it has 4 valence electrons. I have oxygen. I have 2 of those, and each one of those has 6 electrons. Okay, when I go multiply across, I get 4, 12, and my total is 16. So my total, I'm going to add them all up. I get 16 valence electrons. That means I have to use 16 electrons either in a bond or as lone pairs. That's what that means. Okay. Now my least electronegative. Well, carbon is less electronegative than oxygen. So my carbon atom is going to be in the center. Then I'm going to surround it by the 2 oxygens I have. Okay? That's what that means. Least electronegative in the middle, and then your others on the outside. My electronegativity, by the way, for oxygen is 3.5. It has electronegativity of 3.5, each one of these, and we'll talk about that more later. And I know I'll give you a chart for this. This is 2.5. So it shows you also that it's the least electronegative. Okay? And that's the other way to find it. Sometimes they're so close you don't know, and you have to use a chart with the electronegativities to figure it out. So next, we're going to draw, rule 3 says draw a single bond connecting the central atom. Plain and simple. You're going to subtract those bonds from your total. Now, every line represents 2 electrons because they're sharing those 2 electrons. So it's like there's one here, one here, one here, and one here. Okay? So I'm sharing a total of 2, 4. So I'm going to actually subtract 4 from my total. And when I subtract the 4, I get 12 valence electrons. Okay? So that I'm having a running total over here, and I should move this over just a little bit. I'm gonna move it over just a little bit. Only because I'm gonna run out of space is why. So I had 16 valence electrons. I subtracted 4 because I'm using 4 in my model. So I have 12 left. I have 12 electrons that I still have to account for on my model somewhere. So they either have to be bonded or they have to be lone pairs. So that brings me to my next step. Step 5 says add electrons using dots to fill out the outside atoms. No more than 8 for each atom. Okay, so I'm going to start with my outside. I'm going to go, and I'm going to do them in pairs. 2, 4, 6, 8, 10, 12. So, wait, did I do that? I'm just making sure because I have my own notes here. Right, 2, 4, 6, 8, 10, 12. I forgot. I got to put one more. I can't count today, apparently. All right, so that's filling up my outer atoms. Now, number 5 says check for 8 on each atom. So if I go and I check, there's 2, 4, 6, and these 2, this counts as 2. So there's 2 here, 2 here, 2 here, 2 here. There's 2 here, 2 here, 2 here, and 2 here. So this one has 8. This one has 8. I also have to check my central atom. If my central atom right here does not have 8, then I have to do something else. Well, my central atom has 4. So I need a complete octet, and this one does not have a complete octet. So that says, if not a complete octet on each atom, try double bonding and triple bonding if necessary. Okay, you always want to try one before you go to the next one. So let me get rid of this. Okay. So how do I triple bond or double bond? Well, let's go ahead and let's try a double bond. Let's try one double bond. So what I'm going to do is I'm going to take these 2, and one is going to shift here, and it's going to share. So those 2 are going to be shared right here. Well, that puts this now at 2, and here's another 2. So this one now has 8. This one has 8, but this one here has only 6 so far. So let's go ahead and say, I can't do anything with that one because that one's double bonded. So what I'm going to do is I'm going to take this one, and I'm going to do the same thing. I'm going to take 2 electrons and I'm going to share them right here. Now, this one has 2 here. So this one still has 8. This one has 2, 4, 6, 8. Because remember, each line counts as 2. So this one has 8. But now we got to check on this one. 2, 4, 6, 8. 8. Now remember, these lines in the middle represent sharing. And so this line is sharing here and here. So that's how they both get away with having 8. So this is the final product. The final Lewis structure looks like this. And there is your final Lewis structure. Okay? This is a more challenging one because you have the double bonds. Excuse me. Let's do one that's not so challenging. I always start with a more challenging one just because I like to show you the more difficult type ones. This is not as difficult as it can get, but, oh, and I forgot to tell you, every time you use one, you gotta subtract. So I'll do that in this next one, just because I forgot to do it in here and it's already gone. So, all right. So the next one we'll do, and I will show you how we subtract so you can see it. And then I'll go back if I have time and show you how I subtract from there too, from another one that's similar to carbon dioxide. Okay, so let's do NH3. Okay, NH3. Oh, and I also forgot to put something up here. This cannot be hydrogen. Okay, hydrogen can never be a single atom because it only has 1 electron and it can only share 1, and so it can't share with anything else after it's shared. So that's why it cannot be a central atom. So in this case, nitrogen will be the central atom. Okay, nitrogen's a central atom. We're going to add hydrogens around it. And it really doesn't matter where you put it. There's only 3, so you can only add 3. The next step says to draw a single bond. Oh, I did forget one thing. Stop me, Miss Lawson. Okay. Nitrogen has 1, and it has 5 valence electrons. Hydrogen, we have 3 of them, and there's 1 of each of there. So 5 plus 3 is 8 valence electrons. Okay, 8 valence electrons. All right, so we're going to, I forgot that step. We're going to add a bond between each one of these. That's 2. Here's 2, and here's 2. So I'm going to subtract 6. And I get 2 valence electrons left. Okay, so here's where it gets a little tricky. Add to the outer electrons to get no more than 8. Hydrogen cannot have more than 2 at any time. So because hydrogen cannot have more than 2, I can't add any electrons to hydrogen. But if you check to see if everything else has 2, because remember hydrogen is one of those that's weird, and so is helium. This has 2, this has 2, now it has 2. So they're good because it only had that 1 to share. So your other electrons have to pair up here for nitrogen. Okay. When I do that, I'm going to subtract the 2 electrons, and I have 0 valence electrons not being used, which means that everything's there. This has 2, 4, 6, 8. So now this has 8, 2, 2, and 2. That is okay because hydrogen, like I said, can only share 1, and it's good to go. All right, let's do another example. Let's do sorry. Let's do a fun one. NF3, because it's a little bit similar to what we just did, but it's a little different. NF3. Okay, first thing we do is count our valence electron. Again, nitrogen has 1, and we have 5 electrons. We have fluorine, which has 3 of them, and we have 7 valence electrons. So this is 5, and this is 21, for a grand total of 24 valence electrons. Okay, 24 valence electrons. So which one's the central atom? Well, we know fluorine is the most electronegative on my periodic table, and so I'm going to put nitrogen in the middle, and I'm going to add fluorine all the way around it. Doesn't matter where you put the fluorines. Okay. And then I'm going to draw a single bond between each one, and then I'm going to subtract how many I use. So I use 2, 4, 6. So I'm going to subtract 6 from my total, which gives me 18. 18 valence electrons. Okay. Then I'm going to put valence electrons around the fluorines until I get 8. Okay. Remember these count as 2. So I'm going to put 2, 4, 6. 2, 4, 6, because that makes 8. Okay, so this one has 8, because there's 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8. Okay, but that's 8 plus, I mean, sorry, 6, we used 6, 12, 18, right? Somewhere in here. Ah, I can't count. This is not 20, this is 26. That's where I can't count. Y'all are probably going, Miss Lasser, you can't count. And you're yelling at my screen. I just realized what I did. 26, 20. And I knew something wasn't working now. Okay, 20 valence electrons. Okay, so I'm using 18 of them. I have 2 left. I have to use them somewhere. So where's the only place I can use them? Well, this has 8, this has 8, this has 8, but this only has 6. So you can add it to nitrogen. And I apologize for not counting and adding correctly. It's a weekend. Not thinking straight. Okay, so make sure you add correctly, and then make sure that you subtract your final one We use 2 more, so we have 0. You want to make sure you have 0 at the end when you calculate all your stuff. All right, I'm going to do one more, and only because I wanted to show you the double bonds again. And I'm hoping I don't screw this one up, because this one's a little bit more challenging. But it does show up sometimes. This one's going to be fun. I like this one, but it's fun. I just forget it. Okay. SO2. Sulfur dioxide. SO2. SO2. Alright, so first thing we do is count up our valence electrons. We have sulfur, which has 6. Sorry, 1 times 6 is 6. So I'm getting ahead of myself. So you could shorten it. I have oxygen. I have 2 of those times 6, which equals 12. So I have a total of 18 valence electrons. Yell at me through the screen if I did something wrong. But I think I got that one right. Okay. So, which one is the least electronegative? Well, sulfur is the least electronegative. So sulfur goes in the middle. Oxygen goes on the outside. We're going to bond single bonds first. I'm going to subtract the 2 that I used. Sorry, 4 that I used. So that's 12, right? No, it's 14. See, I can't count today. 14 valence electrons. Alright, so then I'm going to add electrons around my outer atoms. 1, 2, 3, 4, 6, 3, 4, 5, 6. Everything has 8 here, but I only used 2, 4, 6, 8, 10, 12. I only used 12, so I have 2 left. If I put them here, like I did with nitrogen, I use my 2, I have 0. This has 8, this has 8, but this only has 6. So I've got to double bond it somewhere. Excuse me. So what do? I go back to the beginning. So I take this way. This is why you want to do it in pencil. Okay. I'm going to take 2 of these and I'm going to share it. So I'll take these 2 off. Okay. And I'm going to double bond right here. This one still has 8. I use 2, 4, 6, 8, 10, 12. So I use 12 again. 2, 4, 6, 8, 10, 12. So I use 12 valence electrons. Okay. And this one has 8. So I have 2 left. This has 2, 4, 6. So if I add 2 electrons here, now I have 8 here. Okay, so I subtract 2. So sometimes you only need one single bond and one double bond. Does it matter which side you go on? No, it really does not. Okay, not in this one. You can go back and forth. It's called a resonance structure. Okay, so if you have any questions, please bring these to class. We're going to do some more in class, but just to give you a foundation, make sure you have your notes over here of what, how to, your rules basically, and then some examples. Okay, have a good day, guys.